The nearest star to Earth, after our Sun, is 4.24 light-years away. Let that sink in for a moment. 4.24 light-years. That's 25 trillion miles. 40 trillion kilometers. If you left Earth today on the fastest spacecraft humanity has ever built, the Parker Solar Probe, traveling at 430,000 miles per hour, you would arrive at that star in approximately 6,700 years. Your great-great-great-grandchildren, 200 generations removed, would be the ones to see it up close. For most of human history, this distance meant the stars were forever beyond our reach. Distant points of light. Beautiful, yes. Inspiring, certainly. But fundamentally unknowable. We could study their light, measure their properties, classify their types, but we could never go there, never see what orbited them, never know if we were alone. But then, in August 2016, everything changed. Astronomers announced they had found a planet orbiting that nearest star. Not just any planet, a rocky world, similar in mass to Earth, orbiting in the habitable zone where liquid water could exist. The closest star to our Sun has a potentially habitable planet. And suddenly, interstellar space wasn't an empty void anymore. It was a neighborhood, with neighbors, with worlds, with possibilities. Here's what we've discovered since then, and I promise you, it's nothing like what we expected. Before we begin our journey, we need to confront a fundamental problem. Human brains are spectacularly bad at comprehending interstellar distances. We can imagine a mile. We can sort of grasp 1,000 miles, maybe even 1,000,000 miles, with effort. But trillions? Our brains just shut down. So let's use an analogy that makes the emptiness visceral. Imagine the Earth is a grain of sand, just a tiny speck, maybe a millimeter across. On that scale, the Sun would be a basketball about 8 feet away from you. Neptune, the outermost planet in our solar system, would be at the far end of a football field, roughly 300 feet away. That's our entire solar system. Everything we've ever explored with spacecraft fits within a football field, with Earth as a grain of sand and the Sun as a basketball. Now, where would the nearest star be? Not across the street, not across town, 500 miles away. If you're in New York, the nearest star would be in Charlotte, North Carolina. If you're in London, it would be in Edinburgh, Scotland. If you're in Tokyo, it would be past Hiroshima. That's how empty space is. For all of human history, this emptiness defined our cosmic loneliness. The stars were unreachable islands separated by oceans of void so vast that even light, the fastest thing in the universe, takes years to cross them. We were trapped in our solar system, looking out at distant lights we could never touch. Even now, with all our technology, our fastest spacecraft would take longer to reach the nearest star than all of recorded human civilization has existed. The journey from the first cities of Mesopotamia to today is about 6,000 years. The journey to the nearest star would take 70,000 years with our current technology. But something changed in the last 30 years. Something that transformed those distant, unreachable points of light into places. Real places, with geography, with weather, with worlds. Let me tell you what we found. The year was 1992. Astronomers Alexander Wolszczan and Dale Frail made an announcement that stunned the scientific community. They had discovered planets orbiting a pulsar, a rapidly spinning neutron star 1,000 light-years from Earth. For the first time in history, we had proof that planets existed beyond our solar system. 3 years later, in 1995, Swiss astronomers Michel Mayor and Didier Queloz discovered the first planet orbiting a Sun-like star, 51 Pegasi b, a hot Jupiter orbiting insanely close to its star. The floodgates opened. By 2009, NASA launched the Kepler Space Telescope with a singular mission: stare at 150,000 stars continuously and watch for the tiny dimming that occurs when a planet passes in front of its star. Over the next decade, Kepler revolutionized our understanding of the universe. By the time it ran out of fuel in 2018, it had discovered over 2,600 confirmed exoplanets and identified thousands more candidates. And the revelation was profound. Planets are everywhere. Not rare, not exceptional, everywhere. Current estimates suggest there is, on average, at least one planet per star in our galaxy. With 200 to 400 billion stars in the Milky Way, that means there are hundreds of billions of planets. Rocky planets like Earth? Estimates suggest tens of billions in our galaxy alone. Planets in habitable zones where liquid water could exist? Billions. The universe we discovered is teeming with worlds. But there was still a problem: distance. The nearest exoplanets Kepler found were hundreds or thousands of light years away. Impossible to study in detail. Impossible to ever reach, even in principle. We knew planets were common, but the closest ones remained mysteries, until we started looking at our nearest stellar neighbors with new instruments, new techniques, and new determination. And what we found changed everything. Because it turns out, you don't need to look thousands of light years away to find other worlds. They're right next door. Over the next hour, we're going to take a journey. Not in spacecraft, not yet, but in imagination and data. We're going to visit the 10 nearest star systems to our Sun, each one within about 11 light years of Earth, each one unique, each one teaching us something profound about the universe we inhabit. And here's what I want you to understand before we begin. These aren't abstract points of light anymore. They're places. Places with names, with characteristics, with histories, with planets in some cases, with futures that will unfold over billions of years. Our journey will take us to Alpha Centauri, a triple star system where the closest star has a potentially habitable planet. Barnard star, an ancient red dwarf racing across the sky faster than any other star, with a super-Earth in its frozen outer reaches. Wolf 359, a flare star capable of emitting intense radiation bursts that could sterilize nearby planets. Lalande 21185, an old wanderer with hints of undiscovered worlds. Sirius, the brightest star in our night sky, a brilliant beacon with a dead white dwarf companion. Luyten 7268, twin flare stars locked in gravitational embrace. Ross 154, a mysterious flaring red dwarf that was once even closer than it is now. Ross 248, a star on approach that will become our closest neighbor in 33,000 years. Epsilon Eridani, a young sun-like star with a planetary system still forming, showing us what our solar system looked like 4 billion years ago. Lacaille 9352, an ancient red dwarf that has witnessed most of cosmic history unfold. At each stop, we'll discover not just what's there, but what it means. What it tells us about stellar evolution, planet formation, the possibilities for life, and the future of human exploration. By the end of this journey, you'll understand something profound. We are not isolated in empty space. We're part of a neighborhood, a cosmic community of stars, all orbiting the galactic center together, all bound by gravity and proximity and shared history. The void between the stars isn't empty. It's full of stories, and we're about to hear them. Let's begin. Our first stop, Alpha Centauri. Distance from Earth, 4.37 light years. That's 25.8 trillion miles. On our scale model, where Earth is a grain of sand and the Sun is a basketball, Alpha Centauri would be 500 miles away. But here's the first surprise. Alpha Centauri isn't one star, it's three. For centuries, we thought it was a single bright star, the third brightest in the night sky, visible only from the southern hemisphere. Ancient astronomers in Greece, Rome, and later Arab civilizations observed it. Ptolemy cataloged it. Renaissance navigators used it. But in 1689, a Jesuit priest named Jean Richaud, observing from Puducherry, India, noticed something remarkable through his telescope. Alpha Centauri was actually two stars, orbiting each other. We call them Alpha Centauri A and Alpha Centauri B. Alpha Centauri A is remarkably similar to our Sun. It's a G-type star, the same classification as our Sun, though slightly larger and brighter. Its mass is about 1.1 times the Sun's mass. Its luminosity is about 1.5 times the Sun's output. Its surface temperature, approximately 5,790 Kelvin, compared to our Sun's 5,778 Kelvin. If you could stand on a planet orbiting Alpha Centauri A, you'd barely notice the difference from our own star. The light would be almost identical, that same warm, yellow-white glow we're accustomed to. The Sun and Alpha Centauri A are cosmic twins, separated by 4.37 light-years but born from similar conditions, evolving along similar paths. Alpha Centauri b is slightly different, a K-type star, cooler and smaller. Its mass is about 0.9 solar masses. Its luminosity about half the Sun's. It glows with a slightly more orange hue. These two stars orbit each other in an elongated ellipse, their separation varying between 11 astronomical units, about Saturn's distance from our Sun, and 36 astronomical units, beyond Neptune's orbit in our system. One complete orbit takes 79.91 years. Imagine looking up from a planet orbiting one of these stars. You'd see your Sun, let's say Alpha Centauri A, blazing in the sky, similar in appearance to our Sun. But you'd also see Alpha Centauri b, sometimes appearing as bright as several hundred full moons combined when at closest approach, sometimes dimmer but still dramatically brighter than any star in our night sky. A binary sunset. Two suns in the sky, one clearly dominant, the other brilliant but secondary. And then there's the third member of this system, the one that changes everything. In 1915, Scottish astronomer Robert Innes, working at the Union Observatory in Johannesburg, South Africa, discovered a faint red star near Alpha Centauri A and B. He measured its position carefully over several months and realized this star was moving across the sky at exactly the same rate as Alpha Centauri A and B. It was gravitationally bound to them. A third member of the system. He named it Proxima Centauri. Proxima meaning nearest in Latin. Because when he calculated its distance, he realized this tiny red dwarf was slightly closer to us than Alpha Centauri A and B. At 4.24 light-years, Proxima Centauri is the closest star to our Sun. But what a strange star it is! Proxima is a red dwarf, an M-type star, the most common type in the galaxy. Its mass is only 0.12 times the Sun's mass, barely massive enough to sustain hydrogen fusion in its core. If it were just a bit smaller, it would be a brown dwarf, a failed star that never quite ignited. Its luminosity is only 0.17% of the Sun's output. If you replace the Sun with Proxima Centauri, Earth would freeze solid within weeks. The star is so faint that despite being the closest star to Earth, it's completely invisible to the naked eye. You need a telescope to see it at all. And it's far from Alpha Centauri A and B, orbiting them at a distance of approximately 13,000 astronomical units. That's 0.21 light-years, or about 1.2 trillion miles. So far out that its orbital period is estimated at 547,000 years. It's barely gravitationally bound at all, just hanging on to the binary pair by the thinnest thread of gravity. For over a century after its discovery, Proxima Centauri was just an astronomical curiosity. The closest star, yes, but unremarkable in every other way. A dim red dwarf, probably alone, probably barren. And then came 2016. August 24, 2016. The European Southern Observatory held a press conference that made headlines around the world. Astronomers had discovered a planet orbiting Proxima Centauri. Not just any planet, an Earth-sized planet. In the habitable zone, the closest exoplanet to Earth. Let me tell you how they found it, because it's a detective story of the highest order. A team led by Guillaume Anglada Escudé used a technique called radial velocity, measuring the tiny wobble in a star's motion caused by an orbiting planet's gravitational pull. As a planet orbits, it tugs on its star, causing the star to move slightly toward us and then slightly away from us. This motion shifts the star's light toward blue when moving toward us, and toward red when moving away by tiny, measurable amounts. The team used the HARP spectrograph, high-accuracy radial velocity planet searcher, on the 3.6-meter telescope at La Silla Observatory in Chile. They observed Proxima Centauri intensively for months, measuring its radial velocity with extraordinary precision. And they found a signal, a regular wobble with a period of 11.2 days. Something was orbiting Proxima Centauri every 11.2 days, tugging it back and forth. And from the strength of that wobble, they could calculate the mass of the orbiting object. 1.17 Earth masses. A rocky planet, possibly with a solid surface, orbiting in the habitable zone of the closest star to our Sun. They named it Proxima b, though some astronomers affectionately call it Proxima Centauri b. Let me paint you a picture of this world, based on what we know and what we can reasonably infer. Proxima b orbits its star at a distance of just 0.05 astronomical units, that's 7.5 million kilometers, or about 4.6 million miles. For comparison, Mercury orbits our Sun at 0.39 astronomical units. Proxima b is 7 times closer to its star than Mercury is to ours. But remember, Proxima Centauri is tiny and dim compared to our Sun. At this distance, Proxima b receives about 65% of the stellar energy that Earth receives from the Sun. Not identical, but within the range where liquid water could theoretically exist on the surface if conditions are right. The planet's orbital period is 11.2 days. That means a year on Proxima b lasts just 11 Earth days. And here's where things get strange. The planet is almost certainly tidally locked. Just like our moon always shows the same face to Earth, Proxima b almost certainly always shows the same face to Proxima Centauri. One hemisphere experiences eternal day, the star frozen in the same position in the sky, never setting. The other hemisphere experiences eternal night, the star never rising, only the distant, faint glow of Alpha Centauri A and B providing any light at all. Imagine standing on the day side. Above you, Proxima Centauri appears about 3 times larger than our Sun appears from Earth, a dull orange-red orb that never moves. The sky would be salmon-colored, tinged with red and orange light. The star doesn't rise or set, it just sits there, motionless, casting eternal shadows that never change. The temperature on this day side would be scorching, hundreds of degrees Celsius if there's no atmosphere to distribute heat. Now walk toward the night side. As you approach the terminator, the boundary between day and night, the temperature drops. The star sinks toward the horizon but never quite disappears. This twilight zone, the ring around the planet where the star eternally sits on the horizon, might be the only habitable region. Cross into the night side completely and you're plunged into darkness. The temperature plummets to potentially hundreds of degrees below zero. The only light comes from the stars, and Alpha Centauri A and B appearing as 2 brilliant points, one slightly brighter than the other, casting faint double shadows. If Proxima b has an atmosphere, and that's a massive if, it would redistribute heat from the day side to the night side. Powerful winds, perhaps hundreds of miles per hour, would constantly blow from hot to cold, trying to equalize the temperature. The terminator zone would be racked by eternal storms. But does Proxima b have an atmosphere? That's the trillion-dollar question. Red dwarfs like Proxima Centauri are highly active in their youth, emitting powerful flares and intense radiation. They produce massive stellar flares, eruptions of energy and radiation that can increase the star's brightness by factors of 10 or more. These flares blast the surrounding space with X-rays, ultraviolet radiation, and charged particles. When Proxima b first formed, 4.85 billion years ago, around the same time Earth formed, it would have been subjected to a hellish bombardment. Young Proxima Centauri would have been far more active than it is today, producing flares constantly, perhaps daily or even hourly. These flares would have stripped away any primordial atmosphere the planet had. Hydrogen, helium, even water vapor, blasted into space by the stellar wind and radiation. Modern observations have confirmed that Proxima Centauri still produces flares. In March 2016, just months before Proxima b's discovery was announced, the star brightened by a factor of 68 in just 10 seconds. A massive superflare releasing more energy in a few seconds than the Sun emits in an entire day. Any atmosphere on Proxima b would need to be constantly replenished by volcanic activity, by comet impacts, by some process that replaces what the stellar wind strips away. So we don't know if Proxima b has air. We don't know if it has water. We don't know if it has any chance of hosting life. But here's what we do know. It's there. It's real. And it's only 4.24 light-years away, the closest potentially habitable world beyond our solar system. And it changed everything about how we think about interstellar exploration. Because now we don't just wonder if there are planets around nearby stars. Now we know, and we have a specific destination. But Proxima Centauri is just one member of the Alpha Centauri system. What about Alpha Centauri A and B, the Sun-like stars? If they have planets, especially habitable ones, the implications are staggering. Sun-like stars are far more stable than red dwarfs. any planets in their habitable zones would receive steady, reliable energy, just like Earth does. The search has been going on for decades. In 2012, astronomers announced they had found a planet orbiting Alpha Centauri b, a small, rocky world in a tight orbit. The discovery made headlines. Planet found around Alpha Centauri? The closest sun-like star had a planet. Except, it didn't. Follow-up observations failed to confirm the signal. By 2015, most astronomers agreed the planet was an artifact of data analysis. A false positive, a ghost in the machine. It was an embarrassing setback, reminiscent of the Barnard's star-planet controversy from the 1960s, which we'll get to shortly, but the search continued using more advanced instruments and techniques. One of the most promising projects is called Near-Earths in the Alpha Centauri region. It's an instrument installed on the Very Large Telescope in Chile, specifically designed to directly image planets around Alpha Centauri A and B. Instead of detecting the tiny wobble a planet causes in its star's motion, NEAR tries to see the planet directly by blocking out the star's light with a coronagraph and looking for the faint thermal glow of the planet itself in infrared wavelengths. In 2021, the NEAR team announced they had detected a candidate signal, possibly a Neptune-sized planet orbiting Alpha Centauri A. But I need to be honest, this detection is extremely preliminary and highly controversial within the astronomy community. The signal is weak, ambiguous, and could easily be instrumental artifacts, background interference, or thermal variations on the telescope itself rather than a real planet. Most astronomers are remaining skeptical and waiting for independent confirmation before accepting it as real. As of now, it's unconfirmed and may never be confirmed. If it is eventually verified, and that's a big if, it would be the first planet detected around a sun-like star in the Alpha Centauri system. But the hunt continues for an even bigger prize, an Earth-sized planet in the habitable zone of Alpha Centauri A or B. The challenge is enormous. Alpha Centauri A and B orbit each other, creating gravitational complexities that make planet formation and stability difficult to model. A planet orbiting one star would be perturbed by the gravity of the other star passing by every 80 years. Some orbits would be stable, others would eject the planet from the system entirely. Computer simulations suggest that planets could exist in stable orbits around either star, particularly in the inner regions, within about 3 astronomical units. The habitable zone of Alpha Centauri A is around 1.25 astronomical units, similar to Earth's position around the Sun. The habitable zone of Alpha Centauri B is closer, around 0.7 astronomical units, but still plausible. If such planets exist, and statistically, they should, given how common planets are, they would be extraordinary targets for study. Imagine a planet like Earth orbiting a star like the Sun just 4.37 light-years away, close enough that, with sufficiently advanced technology, we could send a probe there within a human lifetime, close enough to study in extraordinary detail with next-generation telescopes. The James Webb Space Telescope, launched in 2021, doesn't have the resolution to directly image planets around Alpha Centauri. But future missions might. Concepts like the Habitable Exoplanet Observatory or the Large UV could potentially image Earth-like planets around nearby Sun-like stars and even analyze their atmospheres for signs of life. Alpha Centauri A and B are prime targets. If planets are there, and we suspect they are, we'll find them within the next decade or two. And then humanity will face a choice. Do we just observe from afar, or do we go? Because there's a project already underway, announced in 2016, aimed at sending the first interstellar probes to Alpha Centauri within our lifetimes. It's called Breakthrough Starshot. The concept? Build thousands of tiny spacecraft, each weighing about 1 gram, equipped with cameras and sensors attached to ultra-thin reflective sails. Launch them into space, then hit them with an enormous ground-based laser array. Hundreds of lasers working in concert, focusing petawatts of power on these tiny sails. The light pressure would accelerate the spacecraft to 20% the speed of light, 60,000 kilometers per second, in just a few minutes. At that speed, the journey to Alpha Centauri would take approximately 20 years. 20 years, not 70,000, not generations, within a human lifetime. The spacecraft would fly past Alpha Centauri at 20% light speed, too fast to slow down, but fast enough to snap photographs, take measurements, and send the data back to Earth via laser. Those signals would take another 4.24 years to reach us. So, 24 years after launch, we'd receive the first close-up images of another star system. Images of Proxima b, possibly images of planets around Alpha Centauri A or B. It's ambitious, it's expensive, it's technologically daunting, but it's not science fiction. The physics work. The engineering is challenging but plausible, and Alpha Centauri, our nearest stellar neighbor, is the target. 4.24 light-years. It's the closest any star can be without being part of our solar system. And it's not one star, but 3. And at least one planet, possibly more. A triple-star system with worlds. Our nearest cosmic neighbors. But Alpha Centauri is just the beginning of our journey. Our neighborhood contains wonders far stranger and more diverse than anyone imagined. Let's continue outward. Our second stop takes us slightly farther, 5.96 light-years from Earth. But this star is remarkable not for its proximity, but for its motion. Meet Barnard's star, the fastest-moving star in the night sky. In 1916, American astronomer Edward Emerson Barnard, working at Yerkes Observatory in Wisconsin, was photographing the night sky when he noticed something extraordinary. A faint red star in the constellation Ophiuchus that had moved noticeably compared to photographs taken just a few years earlier. Stars do move through space. They're not fixed points, despite what ancient astronomers believed, but their motions are so slow and their distances so vast that most stars appear stationary over human lifetimes. The constellations our ancestors saw thousands of years ago look essentially the same to us today. But not this star. This star was racing across the sky. Barnard measured its proper motion, the angular speed at which it moves across our field of view, at 10.3 arcseconds per year. To put that in perspective, the full moon appears about 1,800 arcseconds across. This star moves the equivalent of the moon's full diameter every 175 years. In a human lifetime of 80 years, it moves about half a moon width. That might not sound like much, but in astronomical terms, it's blazing fast. No other star moves across the sky as quickly. Why? It's not because Barnard's star is moving unusually fast through space. Its velocity relative to the Sun is about 142 kilometers per second, which is fast but not exceptional. The reason it appears to move so quickly is because it's close. At only 5.96 light-years away, even modest true motion translates into large apparent motion. It's like watching a car drive past you versus watching a plane fly overhead at 30,000 feet. The car might be going slower, but it appears to move faster because it's closer. And here's something remarkable. Barnard's star is approaching us. Right now, it's the second closest star system to Earth, but it's moving closer. In about 9,800 years, practically tomorrow in cosmic terms, it will reach its closest approach, 3.75 light-years from the Sun. At that point, it will be the closest star to our solar system, surpassing even Proxima Centauri. Then it will begin to recede, moving past us and continuing on its journey through the galaxy. We're witnessing a cosmic close encounter in slow motion. But what kind of star is Barnard's star? It's a red dwarf, an M4-type star, slightly larger than Proxima Centauri, but still tiny compared to our Sun. Its mass is about 0.14 solar masses, 14% the mass of the Sun. Its luminosity is a mere 0.35% of the Sun's output. Like Proxima, it's completely invisible to the naked eye despite being the second closest star. But unlike Proxima, Barnard's star is ancient. Current estimates place its age between 7 and 12 billion years old. For comparison, our Sun is 4.6 billion years old. The universe itself is only 13.8 billion years old. Barnard's star formed when the universe was young, possibly before the Milky Way had fully settled into its current spiral structure. It has witnessed nearly the entire history of our galaxy unfold, and it's a metal-poor star, meaning it has relatively few heavy elements compared to stars like the Sun. This confirms its age. It formed from primordial gas that hadn't been enriched by as many generations of supernovae. For over a century, Barnard's star was just a curiosity, the fast-moving ancient red dwarf. Interesting, but not extraordinary. Until 1963, when astronomer Peter van de Camp made an announcement that would reverberate through astronomy for decades. He claimed he had discovered a planet orbiting Barnard's star. Van de Camp worked at Sproul Observatory in Pennsylvania, where he had spent years photographing Barnard's star and measuring its position with extraordinary precision. He claimed to detect a wobble in the star's motion, a tiny oscillation that suggested something massive was orbiting it, tugging it back and forth gravitationally. He calculated the planet's properties, about 1.6 times Jupiter's mass, orbiting every 24 years. The announcement made headlines worldwide. Planet found around nearby star. This was decades before the first confirmed exoplanet discoveries. If true, it would be the first planet ever detected outside our solar system. Astronomers were skeptical but excited. They began their own observations trying to confirm Van de Camp's findings. And they couldn't. No one else could detect the wobble. By the 1970s, the truth emerged. The wobble was an artifact of a telescope adjustment made at Sproul Observatory. The instrument had been recalibrated, introducing a systematic error that Van de Camp mistook for planetary motion. There was no planet. It was a false positive, one of the most famous and embarrassing in the history of astronomy. Van de Camp spent the rest of his career defending his claim, but the astronomical community had moved on. Barnard's star, it seemed, was alone. And then came 2018. A team led by Ignacy Ribas, using modern radial velocity measurements from multiple telescopes, announced they had detected a real planet orbiting Barnard's star. Not the Jupiter-sized world Van de Camp claimed. Something different. Barnard's star, B. Mass, 3.2 times Earth's mass. A super-Earth, larger than our planet, but still rocky. Orbital period, 233 days, about 2/3 of an Earth year. Distance from the star, 0.4 astronomical units, about the distance where Mercury orbits our Sun. Temperature, approximately minus 170 degrees Celsius. It orbits near what's called the snow line, the distance from a star where water freezes solid. Any water on Barnard's star B would be ice, not liquid. The planet is far too cold for life as we know it. But it's there. A planet around the second closest star to Earth. A super-Earth in a frozen orbit around an ancient red dwarf. And here's the kicker. There may be more. Ongoing observations have detected additional signals in the radial velocity data. Hints of other planets, possibly multiple worlds in the system. None confirmed yet, but the data is suggestive. Barnard's star might not be alone after all. It might host a planetary system, cold and dark, worlds locked in orbit around a dim, ancient sun. In 9,800 years, when Barnard's star makes its closest approach to us, it will be only 3.75 light-years away, closer than Alpha Centauri is now. Our descendants, if humanity still exists, if we're still on Earth, will have a new nearest neighbor. An ancient, fast-moving red dwarf with frozen worlds. A cosmic visitor passing through. Let's jump ahead to the fifth closest star system, Wolf 359, at 7.86 light-years from Earth. If you're a Star Trek fan, you might recognize that name. The Battle of Wolf 359, where the Borg destroyed a Federation fleet. The writers chose this star because it's real, nearby, and has a dramatic name. But reality is often stranger than fiction, and Wolf 359 is strange indeed. This star was discovered in 1918 by German astronomer Max Wolf, who was conducting a photographic survey of the sky. He cataloged it as the 359th object in his survey, hence the designation Wolf 359. It's a red dwarf, one of the smallest and dimmest stars capable of sustaining fusion. Its spectral type is M6, putting it near the bottom of the main sequence. Its mass is only 0.09 solar masses, just 9% the mass of our Sun. If it were any smaller, any less massive, it wouldn't be a star at all. It would be a brown dwarf, a failed star that never achieved the core temperatures necessary for sustained hydrogen fusion. But Wolf 359 just barely makes the cut. It's fusing hydrogen, glowing with a faint, dull red light. Its luminosity is a mere 0.09% of the Sun's. making it about 1,100 times fainter than our star. From Earth, even though it's relatively nearby at 7.86 light-years, Wolf 359 is completely invisible to the naked eye. You need at least a modest telescope to see it at all. Wolf 359 is what astronomers call a flare star, a red dwarf that produces frequent, powerful stellar flares. Imagine our sun's surface erupting with a colossal explosion, magnetic field lines snapping and reconnecting, releasing stored energy in a burst of X-rays, ultraviolet radiation, and charged particles. The sun does this occasionally. Solar flares happen during periods of high solar activity. But Wolf 359 does it constantly. And when it flares, it doesn't just increase in brightness by a few percent. It can increase by factors of 3 to 10 in a matter of minutes. A flare that makes the entire star temporarily 10 times brighter. These flares last for hours or even days before the star settles back to its normal dim state. Stars like the Sun have two zones, a radiative core where energy moves outward as photons, and a convective outer layer where hot plasma physically rises and cooler plasma sinks like water boiling in a pot. But small red dwarfs like Wolf 359 are entirely convective. There's no radiative zone. The entire star is churning, roiling plasma, moving heat from core to surface through convection. This creates powerful magnetic fields, tangled, twisted magnetic field lines that store enormous energy. When these field lines snap and reconnect, they release that energy as flares. Young red dwarfs flare almost constantly, multiple times per day, sometimes multiple times per hour. As they age, the flaring gradually decreases, but never completely stops. Wolf 359 is probably several billion years old, not young by stellar standards, but it still flares regularly. And when it does, any planets in the system would be bathed in intense radiation. X-rays, ultraviolet light, high-energy particles screaming out from the star's surface at millions of miles per hour. If you were standing on a planet orbiting Wolf 359, you'd need to be deep underground or underwater during these flares to avoid lethal radiation doses. Any atmosphere the planet had would be gradually stripped away by the stellar wind. The stream of charged particles constantly flowing from the star, amplified dramatically during flares. This is the fundamental problem with red dwarf habitability. The habitable zone, where liquid water could exist, is very close to the star because red dwarfs are so dim. But that proximity puts planets directly in the line of fire during stellar flares. It's like living next to a neighbor who occasionally throws grenades over the fence. Sure, the location is close and convenient, but the explosions are a problem. No planets have been confirmed around Wolf 359 yet. The flare activity makes detection difficult. The flares create noise in the data that can hide or mimic planetary signals. But statistically, it should have planets. Nearly every star does. They're just hidden, waiting to be found. If they exist, they're probably dead worlds, rocky spheres with no atmosphere, their surfaces scoured clean by billions of years of stellar flares. Unless life found a way. Underground caves, subsurface oceans, protected by kilometers of ice, radiation-resistant organisms huddled in the shadows. It's possible. Life is tenacious. But it's a harsh environment. Wolf 359 shows us that not all stars are welcoming. The universe isn't uniformly hospitable. Our fourth stop, Lalande 21185 at 8.29 light-years from Earth. The name is less dramatic than Wolf or Barnard's star, but the history is just as rich. This star was catalogued in 1801 by French astronomer Joseph-Jérôme Lefrançois de Lalande as the 21,185th entry in his comprehensive star catalogue. For over a century, it was just another faint red star in the constellation Ursa Major, the Big Dipper. But in the early 1900s, astronomers noticed something. This star has high proper motion, 4.8 arcseconds per year, making it one of the faster-moving stars in the sky, though not as fast as Barnard's star. High proper motion usually means one thing: the star is close. And indeed, when its distance was measured precisely, Lalande 21185 turned out to be only 8.29 light-years away, the seventh closest star system to the Sun. There are several stars we haven't visited yet that are closer. Lalande 21185 is a red dwarf, spectral type M2, slightly larger and brighter than Wolf 359 or Proxima Centauri. Its mass is about 0.39 solar masses. Its luminosity is about 2% of the Sun's output, and like Barnard's star, it's old. Estimates place its age at somewhere between 5 and 10 billion years. It has been around for most of cosmic history. It's also approaching us. Not as dramatically as Barnard's star, but steadily moving closer. In about 20,000 years, it will pass within 4.65 light-years of the Sun before beginning to recede again. But the real story of Lalande 21185 is about what we thought we found there and how wrong we were. In the 1990s, astronomer George Gatewood claimed to have detected wobbles in Lalande 21,185's position, astrometric variations that suggested multiple planets orbiting the star. He announced the discovery of 2 planets, possibly 3, based on decades of photographic measurements from Allegheny Observatory. The astronomical community was intrigued but cautious. This was before the flood of confirmed exoplanets. Techniques were still being refined, false positives were common. Other astronomers attempted to confirm Gatewood's findings using more modern instruments and methods. They couldn't. The signals vanished when observed with better equipment and techniques. By the early 2000s, the consensus was clear. The claimed planets around Lalande 21185 were artifacts, measurement errors, instrumental noise, wishful thinking perhaps. There were no confirmed planets around Lalande 21185, and to this day that remains true. Despite being one of the closest stars to Earth, despite decades of observations, no planets have been confirmed. But that doesn't mean they're not there. Modern statistical analyses suggest that virtually every star should have planets. The question isn't whether planets exist around Lalande 21185, but whether we've looked hard enough with sensitive enough instruments to detect them. Red dwarfs can have planets that are difficult to detect. If they're not aligned properly for transits, where the planet passes in front of the star from our perspective, and if they're not massive enough to cause large radial velocity wobbles, they can hide. But the next generation of instruments, the James Webb Space Telescope, the extremely large telescope under construction in Chile, upcoming space missions, will have the sensitivity to find even small planets around nearby stars. If Lalande 21185 has planets, we'll likely find them in the next decade or two. And if we do, it will close a chapter that began in the 1990s, a story of claimed discoveries, scientific skepticism, false positives, and ultimately, the truth. Lalande 21185 is a reminder that astronomy is a process. We make claims, we test them, we refine our methods. Sometimes we're wrong. Sometimes we have to wait years or decades for technology to catch up to our questions. But eventually, we get answers. We've now visited 4 star systems: Alpha Centauri, Barnard Star, Wolf 359, and Lalande 21185. We've seen diversity, triple systems and single stars, sun-like stars and red dwarfs, and relatively calm ones. We've seen planets confirmed and planets hiding. But our journey is only half complete. Ahead lies the brightest star in our neighborhood, a cosmic beacon that has captivated humanity for thousands of years. A star with a secret that took centuries to uncover. Let's continue. Our next destination is different from everything we've seen so far. Distance, 8.60 light-years. It's not the closest star we'll visit, but it's the most visible. When you look up at the night sky on a clear winter evening in the northern hemisphere, or almost any evening in the southern hemisphere, there's one star you can't possibly miss. It dominates the sky. It blazes with a brilliant blue-white light that makes every other star look dim by comparison. That's Sirius, the dog star, the brightest star in the night sky besides our sun. And here's what's remarkable. It's not the brightest because it's closest. We've already visited stars much closer: Proxima Centauri, Alpha Centauri, Barnard Star. None of them are visible to the naked eye. Sirius is bright because it's powerful. It's 25 times more luminous than our sun. If you placed it where our sun is, Earth would be instantly vaporized. Even at its actual distance of 8.6 light-years, it outshines every other star in our local neighborhood combined. Ancient civilizations worshipped Sirius. The Egyptians based their calendar on its heliacal rising, the day each year when Sirius first became visible just before dawn, which coincided with the annual flooding of the Nile. They called it Sopdet and associated it with the goddess Isis. The ancient Greeks called it Sirios, meaning scorching or blazing. They noticed that Sirius rose just before the sun during the hottest part of summer, late July through August, and believed its light added to the sun's heat, creating the oppressive dog days of summer. The Romans called it Canicula, the little dog, which is why we still call those hot summer weeks dog days. Every ancient civilization that could see it gave it a name. Every culture watched it. For thousands of years, it was the star, the reference point, the beacon, the most prominent celestial object besides the sun and moon. But what is Sirius? For most of history, we didn't know, just a bright star, nothing more. Then, in 1844, German astronomer Friedrich Bessel made an extraordinary discovery. He was studying Sirius's motion across the sky, measuring its proper motion with extreme precision. And he noticed something odd. Sirius wasn't moving in a straight line. It was wobbling, a tiny oscillation, side to side, superimposed on its overall motion through space. Bessel realized what this meant. Something invisible was orbiting Sirius, a companion star too faint to see, but massive enough to gravitationally tug Sirius back and forth. He predicted the companion's orbital period, approximately 50 years. He calculated its mass, roughly equal to the sun's mass, but no one could see it. Bessel's prediction was based purely on mathematics and observation of Sirius's motion. For 18 years, astronomers searched for this invisible companion, trying to tease it out from Sirius's overwhelming glare. Then, in 1862, American telescope maker Alvin Graham Clark was testing a new 18.5-inch refracting telescope, the largest in the world at the time. He pointed it at Sirius to test the optics, and there, right next to the brilliant glare of Sirius, he saw it, a faint point of light, the companion. Sirius wasn't alone. It was a binary system. They named the bright star Sirius A and the faint companion Sirius B. But when astronomers measured Sirius B's properties, they encountered something bizarre. Its mass was roughly equal to the sun's, just as Bessel had predicted. But its luminosity was only 0.026 times the sun's output. It was incredibly dim for such a massive star. The only way that made sense was if Sirius B was extraordinarily small. Further observations confirmed it. Sirius B is approximately the size of Earth, a star with the sun's mass compressed into a sphere the size of our planet. This was unlike anything astronomers had ever seen, a new type of object. They called it a white dwarf, white because of its color, extremely hot surface temperature around 25,000 Kelvin, dwarf because of its tiny size. Sirius B was the first white dwarf ever discovered, and it changed astronomy forever, because a white dwarf isn't a normal star, it's a corpse. Let me tell you Sirius B's story, and why it explains what we're looking at today. 500 million years ago, the Sirius system looked very different. There were still two stars, gravitationally bound, orbiting each other. But Sirius A, the star we see as brilliant today, was smaller and dimmer, and Sirius B was larger and brighter than Sirius A. Sirius B was originally about 5 solar masses, a massive, hot blue-white star. It blazed brilliantly, living fast and burning through its hydrogen fuel at a furious rate. Massive stars don't live long. The more massive a star, the faster it exhausts its fuel. Our sun will live about 10 billion years. Sirius B, at 5 solar masses, had a lifespan of only about 100 million years. Approximately 120 million years ago, Sirius B ran out of hydrogen in its core. Without fusion to support it against gravity, the core began to collapse. But the collapse heated the core, igniting a shell of hydrogen around it. The star expanded dramatically, swelling into a red giant, a bloated, enormous star with a cool surface but incredible total luminosity. At its maximum size, Sirius B would have been hundreds of times larger than the Sun. If it were where our Sun is, it would have engulfed Mercury, Venus, and possibly Earth. The star's outer layers became unstable. Stellar winds, powerful streams of gas flowing from the surface, began carrying away the outer envelope. Over millions of years, Sirius B shed its outer layers into space, exposing its hot, dense core. And some of that material, perhaps as much as 1 to 2 solar masses, transferred to Sirius A, gravitationally pulled onto the companion star, making Sirius A more massive and more luminous than it would have been alone. Finally, about 120 million years ago, the process completed. The outer layers dispersed into space, forming a planetary nebula, a glowing shell of gas expanding outward. That nebula has long since faded and dispersed. We can't see it today. What remained was the core, a sphere of carbon and oxygen, compressed to incredible densities, no longer fusing elements but glowing white-hot from residual heat. A white dwarf, Sirius B. And here's where things get truly mind-bending. Sirius B has roughly the Sun's mass, about 0.98 solar masses, but it's the size of Earth. 1 teaspoon of Sirius B's material would weigh approximately 10 to 15 tons on Earth. This density is possible because the star is held up not by thermal pressure, like normal stars, but by something called electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed closer together beyond a certain point. The surface temperature is approximately 25,000 Kelvin, nearly 5 times hotter than the Sun's surface. But because Sirius B is so small, its total luminosity is low. Surface area matters. A tiny hot object emits less total energy than a large, cooler object. Sirius B is slowly cooling. Over billions of years, it will radiate away its residual heat, fading from white to yellow to red to, eventually, a black dwarf, a cold, dark cinder of carbon and oxygen drifting through space. But that won't happen for trillions of years. The universe isn't old enough yet for any black dwarfs to exist. Today, Sirius A and Sirius B orbit each other every 50.09 years. Their separation varies from 8.2 to 31.5 astronomical units, swinging from roughly Saturn's distance from our Sun to beyond Neptune's orbit. They're currently near their closest approach, making Sirius B easier to observe, though you still need a powerful telescope to see it through Sirius A's overwhelming glare. So could there be planets around Sirius? Could life exist there? The short answer is almost certainly not. Let's break down why. Problem 1. The system is too young. Sirius A is only about 240 million years old. For comparison, Earth is 4.6 billion years old. Even if planets formed around Sirius A immediately, which they probably didn't, since planet formation takes tens of millions of years, there hasn't been enough time for complex life to evolve. 240 million years ago on Earth, we were in the Triassic period. Dinosaurs were just beginning to appear. Mammals didn't exist yet. Complex multicellular life existed, yes, but nothing resembling human-level intelligence. Sirius A would need to exist for billions more years before its planets, if it has any, could potentially host complex life. Problem 2. The red giant phase. Remember what happened 120 million years ago? Sirius B became a red giant, a star hundreds of times larger than normal, with intense radiation output and powerful stellar winds. Any inner planets around Sirius B would have been engulfed by the expanding star, swallowed whole, vaporized in the star's outer atmosphere. Any outer planets would have been subjected to intense radiation and heat, likely stripping away their atmospheres and sterilizing their surfaces. And this happened only 120 million years ago. Geologically recent. Not enough time for planets to cool, for atmospheres to reform, for life to start over, even if it wanted to. Problem 3. Sirius A's luminosity. Sirius A is an A-type star. It's about twice the mass of the Sun and 25 times more luminous. That means its habitable zone, where liquid water could exist on a planet's surface, is much farther out than Earth's orbit around the Sun. The habitable zone around Sirius A would be approximately 4 to 5 astronomical units from the star, around Jupiter's distance in our solar system. Planets at that distance take much longer to form. They're more likely to be gas giants or ice giants rather than rocky worlds. And even if rocky planets exist there, the intense UV radiation from the hot A-type star would be problematic for life. Problem 4. Sirius A won't live long enough. A-type stars like Sirius A have lifespans of about 1 billion years total. Sirius A is already 240 million years old, roughly 1/4 through its life. In another 700 to 800 million years, Sirius A will run out of hydrogen fuel and begin to expand into a red giant, just like Sirius B did. That's not enough time for complex life to evolve. Earth needed 4 billion years. Sirius A will be a red giant before it reaches even 1 billion years old. So no, Sirius almost certainly doesn't host life. It's too young, too violent in its past, too short-lived in its future. But Sirius isn't about life. It's about stellar evolution. It's about binary dynamics. It's about showing us what happens to stars across different masses and ages. Sirius B shows us the fate of medium-mass stars. Red giant, mass loss, white dwarf, slow cooling over trillions of years. Sirius A shows us a young, vibrant star, bright, hot, living fast. Together, they're a laboratory for understanding stellar physics. And they're close enough to study in detail, close enough to measure precisely, close enough to use as a reference for understanding stars across the galaxy. But Sirius has one more mystery, one that has puzzled astronomers and classical scholars for over a century. Some ancient texts appear to describe Sirius as red, though this is heavily debated and controversial among historians and astronomers. The Greek astronomer Ptolemy, writing in the 2nd century AD, used a Greek color term that some scholars translate as red, seemingly placing Sirius in a similar category as Mars and Betelgeuse. However, ancient Greek color terminology didn't map neatly to modern color categories. The word Ptolemy used could refer to various bright, intense, or fiery colors, not necessarily what we'd call red today. The Roman philosopher Seneca also described Sirius using reddish language, though again, the interpretation is complicated by translation issues and the poetic nature of Roman writing. Other ancient sources, Babylonian, Chinese, Egyptian, contain references that some scholars interpret as describing Sirius with reddish hues. But when we look at Sirius today, it's unmistakably blue-white. There's no hint of red at all. So what happened? Did Sirius change color in the last 2,000 years? This mystery captivated astronomers in the 20th century. Some proposed wild theories. Theory 1. Sirius B was a red giant 2,000 years ago, and ancient observers saw its red light combined with Sirius A's blue-white light, creating a reddish appearance. But the timeline doesn't work. Sirius B became a red giant 120 million years ago, not 2,000 years ago. By Roman times, it was already a white dwarf. Theory 2. Some unknown astrophysical process caused Sirius A itself to temporarily appear red. But stars don't change color on thousand-year timescales. Stellar evolution happens over millions to billions of years. No known process could make an A-type star appear red temporarily. Theory 3. Interstellar dust between us and Sirius caused reddening. But there's no evidence of such dust, and it would have to have cleared away completely in the last 2,000 years. Also implausible. The most likely explanation? A combination of factors. Atmospheric effects. When Sirius is low on the horizon, Earth's atmosphere scatters blue light and transmits more red light, the same reason sunsets appear red. Ancient observers in the Mediterranean would have seen Sirius rising low in the sky during summer, when atmospheric distortion is maximal due to heat. Translation and interpretation errors. Ancient color terms didn't map neatly to modern categories. Red in ancient Greek or Latin could refer to any bright, intense color, including golden yellow or orange. Poetic license. Ancient writers often described bright stars as fiery or burning, using color metaphors that weren't meant to be precise scientific descriptions. So, no, Sirius probably didn't actually change color. It's always been blue-white, or at least for the last several million years. But the controversy shows something important. Astronomy isn't just about modern observations. It's about integrating historical records, understanding how people described what they saw, and recognizing when apparent mysteries might be artifacts of language, culture, and observational conditions. Sirius has been a beacon for humanity for thousands of years. Every civilization that could see it watched it, wondered about it, wove it into their myths and calendars. And now we know what it really is. A young, brilliant star with a dead companion. A binary system showing us stellar evolution in action. a cosmic lighthouse just 8.6 light-years away. Sirius stands apart from the other stars we've visited. It's not a quiet red dwarf, but a blazing blue-white beacon. It's not ancient, but young. It's not alone, but paired with a stellar corpse. Our neighborhood contains extraordinary diversity. Every star tells a different story. And we're only halfway through our journey. Ahead lie binary systems of flaring red dwarfs, a star that will become our closest neighbor in the distant future, and worlds still forming around young suns. Let's continue. Our next destination, 8.73 light-years from Earth. And here, we encounter something we haven't seen yet on our journey. Not just one star, but two stars locked in close gravitational embrace. A binary system of red dwarfs. But these aren't calm, quiet stars. They're among the most brutal objects in our cosmic neighborhood. Meet Luyten 7268, or as astronomers often call them, UV Ceti A and UV Ceti B. This binary system was discovered in 1948 by Dutch-American astronomer Willem Jacob Luyten during his comprehensive survey of stars with high proper motion. He cataloged them as the 726th and 8th entries in his 8th list, hence the designation Luyten 7268. But it was what happened after their discovery that made them famous. In the 1950s, astronomers noticed something extraordinary about the fainter of the two stars, designated UV Ceti B. It would suddenly flare, increasing in brightness by factors of 50 to 100 in a matter of seconds. These weren't small variations. This was the entire star becoming dramatically brighter, then fading back to normal over minutes to hours. It was so distinctive, so dramatic, that UV Ceti B became the prototype for an entire class of variable stars. We now call them UV Ceti variables, or simply flare stars. And Luyten 7268A does it too. Both stars flare, constantly. Let's look at the system more closely. Luyten 7268A is a red dwarf, spectral type M5.5. Its mass is approximately 0.10 solar masses, just 10% the mass of the Sun. It's right on the edge of being able to sustain hydrogen fusion. Any smaller, and it would be a brown dwarf, a failed star. Luyten 7268b, UV Ceti, is even smaller. Spectral type M6, mass approximately 0.09 solar masses. It's one of the smallest true stars known. Both are completely invisible to the naked eye despite being relatively nearby. You'd need at least a small telescope to see them at all. These two tiny stars orbit each other at a separation of only 2.1 astronomical units, less than the distance from the Sun to Mars. They complete one orbit every 26.5 years. If you could stand on a planet orbiting one of these stars, the other star would appear as a brilliant orange-red disk in the sky, hundreds of times brighter than the full moon appears from Earth. Two dim suns, locked in eternal dance. But the real show is the flares. UV Ceti B can increase in brightness by up to 75 times its normal output in a matter of seconds. Imagine, the star is glowing dimly, barely visible. Then suddenly, flash. It brightens dramatically, outshining even its companion star for a brief period. The flare lasts minutes to hours, then fades. The star returns to its normal dim state, and this happens multiple times per day. Both stars show this behavior, though UV Ceti B is more active. Some days, observers have recorded multiple flares from the same star. Why does this happen? Red dwarfs, especially small ones like these, are completely convective. Unlike the Sun, which has a radiative core and a convective outer layer, red dwarfs are convective throughout. The entire star is churning, roiling, mixing hot plasma from core to surface and back. This creates incredibly powerful magnetic fields. The convective motion acts like a dynamo, generating magnetic field lines that thread through and around the star. These magnetic field lines store enormous amounts of energy, like springs being compressed. Eventually, they become so twisted and tangled that they snap. The field lines reconnect in a process called magnetic reconnection, releasing all that stored energy in an instant. The result? A flare. The surface brightens dramatically. X-rays and ultraviolet radiation flood outward. Charged particles, protons and electrons, are accelerated to near light speed and flung into space. It's the same basic process that causes solar flares on our sun, but red dwarfs do it far more frequently and with far more energy relative to their size. Young red dwarfs are the worst. When they first form, they flare almost constantly, multiple times per hour sometimes. As they age over billions of years, the flaring gradually decreases, but it never completely stops. Luyten 726-8A and B are probably several billion years old, middle-aged by stellar standards, and yet they still flare regularly. Now imagine you're on a planet orbiting one of these stars. The habitable zone, where liquid water could exist, would be very close to the star. Red dwarfs are so dim that planets need to orbit close to receive enough heat. For Luyten 7268A or B, the habitable zone would be only about 0.03 astronomical units from the star, approximately 4.5 million kilometers, or about 2.8 million miles. That's only about 12 times the distance from Earth to our moon. Incredibly close. At that distance, the star would appear enormous in the sky, perhaps 40 to 50 times larger than the sun appears from Earth. It would dominate the sky, an orange-red disk taking up a significant portion of the horizon. And the planet would almost certainly be tidally locked, rotating once per orbit so that one side always faces the star, eternal day, and the other side always faces away, eternal night. But then, flare. The star brightens dramatically. Radiation floods the day side of the planet. If you were standing there, you'd be hit by intense X-rays and UV radiation, lethal doses if you weren't protected by a thick atmosphere or underground shelter. The stellar wind, normally a steady stream of charged particles, becomes a gale. Protons and electrons smash into the planet's magnetic field, if it has one, and atmosphere, if it has one, stripping away atmospheric particles molecule by molecule. Over billions of years, this constant bombardment would strip away any atmosphere the planet once had, leaving behind a barren, airless rock. Could life survive? Maybe. Deep underground, protected by kilometers of rock. In subsurface oceans beneath ice caps on the night side. In caves, in crevices, in any place that offers shelter from the radiation. But it would be hard. Life would need to be radiation resistant, capable of repairing DNA damage constantly, adapted to an environment of periodic radiation storms. No planets have been confirmed around Luyten 7268 yet. The flare activity makes detection difficult. The brightness variations from flares can mimic or hide the signals of orbiting planets, but they're there. Statistically, they must be. Nearly every star has planets. If they exist, they're worlds of extremes, eternal day and eternal night. Calm periods and radiation storms. Luyten 7268 shows us that binary stars aren't just twice the complexity, twice the radiation, twice the challenges for any life that might exist. Let's continue to our next destination. Ross 154 at 9.69 light-years from Earth. This star was discovered in 1925 by American astronomer Frank Elmore Ross during his photographic survey of stars with high proper motion. It's the 154th entry in his catalog. Ross 154 is a red dwarf, spectral type M3.5, slightly larger and brighter than the previous red dwarfs we visited, but still small by stellar standards. Its mass is approximately 0.17 solar masses, and like Wolf 359 and Luyten 7268, it's a flare star. Not as active as UV Ceti, its flares are less frequent and less intense, but it still produces powerful stellar flares that can double or triple its brightness within minutes. What makes Ross 154 particularly interesting is its motion. It has a proper motion of approximately 0.7 arcseconds per year. Not as fast as Barnard's star, but still significant. It's moving through space at about 10.5 kilometers per second relative to the Sun. But here's the twist. It's receding from us, not approaching. Right now, Ross 154 is 9.69 light-years away, making it the 10th closest star system. But it's moving away. In the past, it was even closer. Calculations show that approximately 105,000 years ago, when Homo sapiens were just beginning to spread across Africa, Ross 154 made its closest approach to our solar system. At that time, it was only about 6.8 light-years away, making it the sixth closest star to the Sun. Our ancestors, looking up at the night sky with naked eyes, couldn't see it. It's too faint, but it was there, closer than it is now, one of our nearest neighbors. Then it continued on its journey through the galaxy, moving away from us. By 100,000 years from now, it will be over 11 light-years away, slipping farther down the list of nearby stars. This highlights something important. Our stellar neighborhood is temporary. Stars are in motion. They orbit the galactic center at different speeds, in different directions, passing each other like ships in the night. The stars that are closest to us now won't be closest in 1,000,000 years. And 1,000,000 years ago, the neighborhood looked different. The constellations our ancestors saw 100,000 years ago were noticeably different from what we see today. Stars had moved. Some were brighter, closer, some were dimmer, farther. In another 100,000 years, the constellations will be different again. The Big Dipper will look distorted. Orion will be misshapen. The familiar patterns will be gone. Ross 154 is a reminder that we're witnessing a snapshot in time, a temporary configuration of stars that will never exist again. As for planets around Ross 154, none confirmed yet. The flare activity complicates detection, just as with Wolf 359 and Luyten 7268. But ongoing surveys continue to observe it. The TESS mission, Transiting Exoplanet Survey Satellite, has been watching Ross 154, looking for the telltale dips in brightness that would indicate a planet passing in front of the star. If planets are there, we'll find them, eventually. Our final stop in this act, Ross 248, currently 10.29 light-years from Earth. At first glance, it seems like just another red dwarf. Spectral type M5.5, mass approximately 0.12 solar masses, similar in size to Proxima Centauri. Discovered by Frank Elmore Ross in 1925, like Ross 154. But Ross 248 has a remarkable destiny. It's approaching us, rapidly. Right now, it's the 11th closest star system to our Sun. But it's moving through space on a trajectory that will bring it much closer. In approximately 33,000 years, around the year 35,000 AD, Ross 248 will pass within 3.02 light-years of the Sun. At that point, it will be the closest star to our solar system. Closer than Proxima Centauri is now. Closer than Alpha Centauri. Closer than any star in recorded human history. For a period of several thousand years, Ross 248 will hold the title of nearest star. Then it will continue on its path, receding from us, eventually becoming just another distant point of light. This is extraordinary when you think about it. Our descendants, if humanity still exists, if we're still on Earth, will have a different nearest neighbor than we do. The star charts will need to be updated. The target for first interstellar missions might change. The star that dominates discussions of nearby exoplanets will shift. Ross 248 approaching. Proxima Centauri receding very slowly. Barnard star approaching even more dramatically. The neighborhood is in flux. But what do we know about Ross 248 itself? It's a flare star like so many red dwarfs we've visited. Not as active as UV Ceti, but still prone to occasional powerful flares. It's very faint, invisible to the naked eye, requiring at least a small telescope to observe. And no planets have been confirmed around it yet. But as it approaches over the next 30,000 years, it will become easier to study. Closer means brighter. Brighter means easier to detect planets, characterize atmospheres, understand its properties in detail. If Ross 248 has planets, they'll become some of the most accessible worlds for future observations and potentially exploration. Imagine, the year is 35,000 AD. Humanity has survived the next 30,000 years of history. Wars, climate changes, technological revolutions, perhaps even off-world colonization. Our descendants look up at the night sky. The constellations are distorted. The familiar patterns are gone. The stars have moved. And the nearest star, the closest possible destination for interstellar travel, is Ross 248, a red dwarf that wasn't even discovered until 1925. A star that in the 21st century was just a faint point of light 10 light-years away, unremarkable except for its trajectory. Now it's the nearest, the primary target, the destination. What will they find there? Planets, certainly. Statistics virtually guarantee it. Habitable worlds? Maybe. Life? Who knows? But it will be ours to explore if we survive long enough to do so. Ross 248 is a reminder that the universe is not static. The cosmos changes, stars move, neighborhoods evolve, and the future is full of possibilities we can barely imagine. We've now visited 8 star systems. We've seen extraordinary diversity, triple systems and binaries, sun-like stars and tiny red dwarfs, stellar corpses. But our journey still has 2 more stops. Ahead lie a young planetary system still forming, showing us what our solar system looked like billions of years ago, and an ancient red dwarf that has witnessed nearly the entire history of the cosmos. The youngest and the oldest, the beginning and the endurance. Let's continue. Our next destination is different from every star we've visited so far. Distance: 10.52 light-years. It's not the closest. It's not the brightest. It's not the most massive, but it's the most important, at least for understanding where we came from. Because Epsilon Eridani is young, very young, only about 800 million years old, and it has a planetary system still forming, still evolving. When we look at Epsilon Eridani, we're looking at what our own solar system looked like approximately 3.8 billion years ago, when Earth was still being bombarded by asteroids and comets, when the moon was forming from a massive impact, when life was just beginning to emerge in Earth's oceans. Let me introduce you to this remarkable star. Epsilon Eridani is a K-type star, spectral classification K2V. It's slightly cooler and smaller than our Sun, with about 0.82 solar masses and roughly 34% of the Sun's luminosity. But unlike the Sun, which is 4.6 billion years old and settled into middle age, Epsilon Eridani is still in its stellar youth. It's active, dynamic, covered in star spots, the stellar equivalent of sunspots, producing frequent stellar flares, and rotating rapidly, once every 11.2 days compared to the Sun's 25-day rotation period. It's a star with energy to burn, still settling into its long main sequence lifetime, and it's visible to the naked eye. From Earth, it appears as a third-magnitude star in the constellation Eridanus, the river. You don't need a telescope. On a clear night, away from city lights, you can see it, a faint orange point among thousands of other stars. But what you can't see with your eyes is what makes Epsilon Eridani extraordinary. In 2000, astronomers announced they had detected a planet orbiting Epsilon Eridani using radial velocity measurements, the wobble technique we discussed earlier. Epsilon Eridani B mass estimates range from about 0.6 to 1.55 Jupiter masses, a pretty wide range. The uncertainty comes from not knowing the planet's orbital inclination relative to our line of sight. It's definitely a gas giant, somewhere between Saturn and Jupiter in mass, but exactly where in that range is still being refined. Orbital period: approximately 7 to 8 years. Different observational studies have given slightly different values as they collect more data. Distance from the star: around 3.3 to 3.5 astronomical units, comparable to where the asteroid belt sits in our solar system, between Mars and Jupiter. Eccentricity: estimates range from 0.25 to 0.7, meaning the orbit is definitely elliptical rather than circular, but exactly how elongated that ellipse is remains uncertain. The planet's distance from its star varies significantly during each orbit. This is interesting because Jupiter's orbit around our Sun is nearly circular, eccentricity only 0.048. Epsilon Eridani B's more eccentric orbit suggests the planetary system is still dynamically evolving, planets gravitationally interacting, orbits not yet fully settled. But the planet isn't the most interesting thing about this system. In the mid-2000s, astronomers using infrared telescopes detected something remarkable: a debris disk surrounding Epsilon Eridani. Not just one disk, two. The inner disk is located at approximately 3 astronomical units from the star, right around where Epsilon Eridani B orbits. It's composed of dust and small rocky fragments, analogous to our solar system's asteroid belt. The outer disk is located at approximately 20 astronomical units from the star, similar in position to our solar system's Kuiper belt, the region beyond Neptune where objects like Pluto orbit. But here's what's striking. These debris disks are much more massive than the asteroid belt or Kuiper belt in our solar system. There's far more material, dust, rocks, icy bodies, than exists in the equivalent regions around our Sun. Why? Because the system is young. These are the leftovers from planet formation, material that hasn't yet been swept up into planets, ejected from the system, or ground down to undetectable dust. Our solar system had similar debris disks 4 billion years ago. Over time, most of that material was incorporated into planets, ejected by gravitational interactions, or pulverized by collisions into dust so fine it's virtually invisible. Epsilon Eridani still has its debris. The planets are still clearing their orbits. The system is still violent and chaotic. Evidence suggests there might be additional planets in the system, unconfirmed but hinted at by gaps and structures in the debris disks. Possibly a second gas giant at 40 astronomical units, roughly where Uranus orbits in our solar system. If you could stand on a planet in the habitable zone of Epsilon Eridani, roughly 0.5 to 1 astronomical unit from the star, here's what you'd see. The star would appear slightly smaller and dimmer than our Sun appears from Earth, glowing with a faint orange hue. But the sky would be different, scattered throughout the zodiac. The band of sky where planets and the Sun appear to move, you'd see faint dusty streaks, remnants of the debris disk edge on. Not bright enough to dominate the sky, but noticeable. And periodically, perhaps every few months or years, you'd witness spectacular meteor showers as streams of comets and asteroids intersect the planet's orbit. Far more intense than anything Earth experiences today. The sky would occasionally be lit by impacts, asteroids and comets striking moons, or even the planet itself. If you were on an Earth-like world in this system, you'd be living through the equivalent of the late heavy bombardment, the period 4 billion years ago when the inner solar system was pummeled by impacts. Life could potentially exist. Simple microbial life, perhaps, hiding in protected environments. But complex life would struggle under constant bombardment. Epsilon Eridani is a world of potential, not yet realized. A planetary system still under construction, and it's a laboratory for understanding our own origins. By studying Epsilon Eridani, we learn how planetary systems form, how debris disks evolve, how gas giants clear their orbits, how rocky planets might form in the inner system. It's a time capsule, a window into the past, a glimpse of what Earth's neighborhood looked like when life was just beginning. Our final destination, Lacaille 9352, at 10.74 light-years from Earth. After visiting the youngest nearby star, we now visit one of the oldest. This star was catalogued in 1752 by French astronomer Nicolas Louis de Lacaille during his observation campaign in South Africa. He was mapping the southern skies, cataloging thousands of stars never before systematically recorded by European astronomers. Lacaille 9352 was the 9,352nd entry in his catalog. For over 2 centuries, it was just a number, another faint red star among thousands. But modern observations have revealed something extraordinary about this star. It's ancient. Age estimates place Lacaille 9352 at somewhere between 8 and 12 billion years old. Let me put that in context. The universe is 13.8 billion years old. The Milky Way galaxy formed about 13.6 billion years ago. Our Sun is 4.6 billion years old. Lacaille 9352 may have formed when the universe was less than 2 billion years old, when the Milky Way was still settling into its spiral structure, when most of the galaxy was young and turbulent. It has witnessed nearly the entire history of the cosmos. When Lacaille 9352 formed, there were no stars like our Sun in the universe yet. The first generation of stars, made of pure hydrogen and helium, had lived and died, enriching space with the first heavy elements. Lacaille 9352 formed from that enriched material, part of the second or third generation of stars. It has orbited the galactic center approximately 50 to 60 times since it formed. Each orbit takes about 225 million years. It has seen the galaxy evolve, seen stars born and die by the billions, seen our solar system form 4.6 billion years ago as just one more speck in the galactic disk. And it's still here, still fusing hydrogen, still glowing. Lacaille 9352 is a red dwarf, spectral type M1.5, slightly larger and brighter than Proxima Centauri or Ross 248, but still small. Its mass is approximately 0.50 solar masses. Its luminosity is about 2.3% of the Sun's, and because it's a red dwarf, it will continue fusing hydrogen for trillions of years. Red dwarfs are the longest-lived stars in the universe. The smallest ones, like Proxima Centauri, will live for 4 trillion years or more. That's 300 times longer than the current age of the universe. No red dwarf has ever died of old age. None ever will in the current age of the cosmos. They're just getting started. Lacaille 9352 has already lived for up to 12 billion years. It has trillions more to go. By the time it exhausts its hydrogen fuel and fades to a white dwarf, the universe will be unrecognizably different. The Sun will have been dead for trillions of years. Most of the stars visible in today's night sky will be gone, either exploded as supernovae or faded to white dwarfs. Galaxies will have merged. The Milky Way and Andromeda will be long united into Milkomeda. Dark energy will have pushed most other galaxies beyond the cosmic horizon, invisible forever. Lacaille 9352 will still be shining. But does it have planets? Over the years, there have been hints in radial velocity measurements, subtle wobbles that might indicate planets orbiting Lacaille 9352. But here's the truth. As of now, no planets around this star have been confirmed. The signals in the data are ambiguous and could just as easily be caused by stellar activity, spots, flares, or convective motion on the star's surface, rather than actual planets tugging on the star. If future observations with more sensitive instruments do eventually confirm a planet exists, preliminary estimates suggest it might be a super-Earth of around 3 to 4 Earth masses, possibly orbiting in or near the habitable zone with a period of several months. But right now, that's speculation based on uncertain data, not confirmed fact. And here's what makes the possibility profound. If a habitable planet were eventually discovered around Lacaille 9352, and that's still a big if, it could have been potentially habitable for billions of years longer than Earth. Earth is 4.6 billion years old. Life appeared relatively quickly, within a few hundred million years. Complex multicellular life took about 3.5 billion more years to evolve. Intelligent life emerged only in the last few million years. If life formed there early, say 10 billion years ago, it would have had twice as long as Earth life to evolve, diversify, become complex, develop intelligence. What could life accomplish given 10 billion years of evolution? We can barely imagine. On Earth, the leap from single cells to humans took 4 billion years. Given 10 billion years, what forms might life take? What levels of complexity, intelligence, technology? It's almost certainly pure speculation. We don't even know if the planet exists, let alone if it has life. But the possibility is staggering. We've completed our journey through the nearest stars, 10 systems, 13 individual stars, worlds confirmed and worlds yet to be discovered. But what does it all mean? Let me tell you what this journey has taught. The Copernican lesson continues. 400 years ago, Copernicus taught us that Earth isn't the center of the solar system. The Sun is. We orbit it, not the other way around. A century ago, Harlow Shapley taught us that our solar system isn't at the center of the Milky Way. We're out in the suburbs, 2/3 of the way from the center to the edge. 50 years ago, we learned that the Milky Way isn't at the center of the universe. There is no center. All galaxies are moving away from each other in the expansion of space. And now, we're learning the final humbling lesson. Our Sun, the star we thought was typical, average, unremarkable, is actually unusual. Sun-like stars make up only 7 to 8% of all stars in the galaxy. The typical star is a red dwarf, small, dim, long-lived. Stars like Proxima Centauri, Wolf 359, Barnard's star. Most stars aren't alone. They're in binary or multiple systems. Our single sun is the exception. Most planetary systems aren't calm and stable like ours, chaotic, still forming, or already disrupted by stellar evolution. Earth's circumstances, orbiting a single, stable, middle-aged sun-like star with a protective gas giant and a large moon, are rare. We're not typical. We're fortunate. We're the exception, not the rule. And yet, diversity is the true rule. No two star systems are alike. Each has its own history, its own characteristics, its own quirks. Young systems like Epsilon Eridani, still forming, debris disks thick with material. Flare stars like Wolf 359 and UV Ceti, blasting their surroundings with radiation. Calm stars like Alpha Centauri A, stable and sun-like, potential homes for Earth-like worlds. Dead stars like Sirius B, stellar corpses glowing with residual heat. Reminders of mortality even on cosmic scales. The universe isn't uniform, it's not monotonous. It's a tapestry of extraordinary diversity where every star tells a different story. Planets are everywhere. For most of human history, we had no proof that planets existed beyond our solar system. They were theoretical, possible but unconfirmed. Now we know. Planets are the norm. Nearly every star has them. They're as common as stars themselves. Within 10 light-years of the Sun, we've confirmed planets around multiple systems, with hints and possibilities around many others. Scale that up across the galaxy. With 200 to 400 billion stars, there are hundreds of billions of planets, tens of billions of rocky planets, billions in habitable zones. The universe is full of worlds, full of them. And that means the question, are we alone? Has shifted. It's no longer, are there other worlds? But, are there other worlds with life? And if life exists elsewhere, is it common? Or does Earth's particular combination of factors make life extraordinarily rare? The habitability puzzle. Here's what we've learned. Many planets exist, but few are ideal. Red dwarf planets face tidal locking and atmospheric stripping. Survival is possible, but hard. Young systems face constant bombardment from asteroids and comets. Life might form but struggle to become complex before the next impact resets everything. Binary systems face gravitational chaos. Orbits can be unstable. Planets might be ejected entirely. Ancient systems might have lost their atmospheres billions of years ago, leaving behind dead worlds. Earth's circumstances, orbiting a single, stable, calm, middle-aged sun-like star with a protective Jupiter and a stabilizing moon, begin to look less like typical and more like rare. Not unique, perhaps. With billions of planets, even rare configuration should occur millions of times. The search for life isn't just about finding planets in habitable zones. It's about finding planets in habitable zones around stable stars, with protective planetary architectures, with atmospheres that have survived, with time for life to evolve complexity. That narrows the candidates significantly, but not to zero. Never to zero. The numbers are still large, the possibilities still vast. The search continues. Here's what I want you to understand, really understand, as we close this journey. The stars are not distant abstractions. They're not just points of light in the night sky. They're places, real places, with physical properties, with histories, with futures unfolding over billions of years. With planets, worlds of rock and ice and gas, each unique. Possibly with life, evolving in environments we can barely imagine. Proxima Centauri isn't just the nearest star. It's a red dwarf with a planet that might have oceans, might have continents, might have life swimming in subsurface seas, protected from stellar flares by kilometers of ice. Barnard's star isn't just the fast-moving star. It's an ancient wanderer that will pass us in 10,000 years, a star that has orbited the galaxy 50 times, carrying its frozen super-Earth through the cosmic dark. Epsilon Eridani isn't just a young star. It's a planetary system under construction, showing us what our solar system looked like when Earth was young and life was just beginning. Sirius isn't just the bright star, it's a binary system where one star has already lived and died, leaving behind a white dwarf, a glimpse of our own sun's distant future. These are neighbors, not metaphorically. Actually, we share the Milky Way with them. We orbit the galactic center together, all of us bound by gravity, all moving through space on our long, slow journeys around the galaxy. And the neighborhood is dynamic. Stars move. Ross 248 approaches, destined to become our closest neighbor in 33,000 years. Barnard's star races toward its closest approach in 10,000 years. Ross 154 recedes, moving away from us, having made its closest pass 105,000 years ago. The constellations are not eternal. The patterns in the sky our ancestors saw were different from ours. The patterns our descendants will see will be different still. We're witnessing a snapshot, a temporary configuration that will never exist again. 1 million years ago, different stars were closest. 1 million years from now, different stars will be closest. The neighborhood changes, evolves, flows like water. But for now, for this brief moment in cosmic history, these are our neighbors. Alpha Centauri, Barnard star, Wolf 359, Lalande 21185, Sirius, Luyten 7268, Ross 154, Ross 248, Epsilon Eridani, Lacaille 9352, and Proxima Centauri, 4.24 light-years away, with its potentially habitable planet, the closest world beyond our solar system, our nearest cosmic neighbor. The journey to the nearest stars has already begun. It didn't begin with rockets or lasers or nuclear bombs. It began with curiosity, with someone looking up at the sky and asking, "What are those lights? How far away are they? Do they have worlds like ours?" It continued with telescopes, Galileo pointing his crude instrument at the heavens, Edwin Hubble measuring the distance to Andromeda, Harlow Shapley mapping the galaxy's structure. It accelerated with space probes, Voyager 1 and 2, now in interstellar space, carrying golden records with greetings from humanity to whoever might find them. It transformed with the exoplanet revolution, Michel Mayor and Didier Queloz finding the first planet around a sun-like star, Kepler discovering thousands more, TESS surveying the entire sky. And it continues now as we build the next generation of telescopes that will characterize atmospheres, search for biosignatures, perhaps even image other worlds directly. The journey will culminate, perhaps in our lifetimes, perhaps in our children's, with spacecraft. Tiny nanocraft pushed by lasers, accelerating to 20% light speed, flying past Alpha Centauri and sending back the first close-up images of another star system. Or maybe, if we're bold enough, with crewed missions. Generation ships carrying thousands of people across the interstellar void, journeys spanning centuries but ending with human footsteps on alien soil. I don't know if I'll live to see it. You might. Your children almost certainly will. But one thing is certain. The journey has begun. And it won't stop. Because we're curious. We're explorers. We're builders and dreamers and scientists and poets. We look up at the night sky and we don't see distant lights. We see destinations, places to go, mysteries to solve, worlds to discover. The stars are calling. They've always been calling. And for the first time in human history, we're learning how to answer. You are living at the beginning of interstellar exploration, the beginning of understanding our cosmic neighborhood, the beginning of answering the oldest question, are we alone? The stars are not unreachable. They're just very far. But distance is a challenge, not a barrier. And humanity has always been good at overcoming challenges. Tonight, when you look up, remember, you're not looking at distant abstractions. You're looking at places, worlds waiting, neighbors we haven't met yet. The journey to the nearest stars isn't science fiction. It's our future, and it starts now. Tonight, definitely tonight, go outside and look up. Let me help you find the neighbors we've visited. If you're in the northern hemisphere, look south on a winter evening. Find the brightest star in the sky, that brilliant blue-white point that dominates everything around it. That's Sirius, 8.6 light-years away. A binary system where one star has already died and left behind a white dwarf. You're seeing our sun's distant future. In autumn and winter, look for the constellation Eridanus, the river. Epsilon Eridani is visible as a faint orange point, about third magnitude. You can see it with naked eyes if you're away from city lights. That star is only 800 million years old, with a planetary system still forming. You're seeing what our solar system looked like when Earth was young. If you're in the southern hemisphere, look toward the constellation Centaurus, the third brightest star in the night sky, actually two stars, Alpha Centauri A and B, orbiting each other, 4.37 light-years away. Just beyond it, invisible to your eye, is Proxima Centauri with its potentially habitable planet Proxima b. The closest world beyond our solar system. What you're really seeing. When you see these stars, remember, their light has traveled for years to reach you. Sirius's light left that star in 2016. Alpha Centauri's light left in 2020. You're not seeing them as they are now. You're seeing them as they were, and they're moving. Barnard's star is approaching, counting down to its closest pass in 10,000 years. Ross 248 is approaching even more dramatically, destined to become our closest neighbor in 33,000 years. Ross 154 is receding, moving away from us. The sky is not fixed. The stars are ships passing in the cosmic night, each on its own journey through the galaxy. The constellations will change. In 50,000 years, they'll be unrecognizable. The familiar patterns, the Big Dipper, Orion, the Southern Cross, will be distorted, altered by the motion of individual stars. But right now, tonight, you can see the neighborhood as it is, as we experience it. This specific arrangement of stars that will never exist again. This journey through our stellar neighborhood is just beginning. In the next few years, JWST will characterize the atmospheres of nearby exoplanets. We'll know if Proxima b has air, if Barnard's star B has chemistry hinting at geological activity, if any of these worlds show signs of life. In the next decade, the extremely large telescope will begin operations. It might directly image planets around the nearest stars, actual photographs, not just artists' conceptions. We'll see them with our own eyes, or at least through our instruments. In the 2040s or 2050s, if Breakthrough Starshot succeeds, we might launch the first interstellar probes. Tiny spacecraft accelerated to 20% light speed by lasers, flying past Alpha Centauri and sending back humanity's first close-up images of another star system. In the 2060s or 2070s, those images would arrive. People alive today, maybe you, if you're young, might see them. And beyond that? Who knows? Perhaps crewed missions in the 22nd century. Perhaps colonies on planets around other stars in the 23rd. Perhaps a network of human civilizations spanning dozens of star systems by the 24th or 25th centuries. Or perhaps none of that. Perhaps we stay on Earth, content to observe from afar, to study but not visit, to wonder but not wander. But I don't think so. Humanity has always been curious, always been explorers, always looked at the horizon and asked, what's beyond? The horizon now stretches across light years. The journey will take generations, centuries, perhaps millennia, but it will happen, because that's who we are. The journey to the nearest stars isn't just about spacecraft and technology, it's about curiosity, about the fundamental human drive to explore, to discover, to know. And that drive is unstoppable. If you've made it this far, thank you, truly. You've just traveled across light years, visited 10 star systems, and contemplated the deepest questions. What's out there? Could we reach it? Not just Earth, not just the solar system, but this corner of the galaxy, this neighborhood of stars, this cosmic community we share with Proxima, Barnard's star, Sirius, and all the rest. We're not isolated. We're not alone in the void. We're part of something vast and beautiful and full of possibility. Subscribe if you want more journeys through our cosmic neighborhood. Comment with which star you'd most want to visit. Share this with someone who needs to remember that we're part of something extraordinary. And tonight, definitely tonight, look up. Find Alpha Centauri if you're in the southern hemisphere. Find Sirius blazing in the winter sky if you're in the north. Find Epsilon Eridani with binoculars if you can. And remember, those aren't just lights. They're places, worlds waiting to be explored, neighbors waiting to be known. The journey to the nearest stars isn't science fiction anymore.